So we're going to look at carbon-hydrogen combustion analysis. This is done generally with organic compounds, and frequently we are looking for the empirical formula this way. The three big ones we come across are hydrogen, carbon, and oxygen. There could be obviously other things present in that organic compound, but this would not be the best way to do that, or at least in the three-cell model that we discussed in class. So we know the sample is 20 grams, and we know that when it's combusted, we're going to get 17.20 grams of water and 58.74 grams of carbon dioxide. So we don't really know what the formula is, but we do know it's been combusted, and it's produced those products. Now I have 17.20 grams of water and 58.74 grams of CO2. Well, when we do this, we have to remember that we have added oxygen to this mixture. So the 58.74 grams includes oxygen that could have been in the compound or could have been added as a second reactant. So really all we can focus on for this type of problem is we can focus on the carbon and the hydrogen, because those things only possibly could have come from our sample. So how we go about this is we look at the percent composition of carbon dioxide for carbon, and water, we look at hydrogen. So percent carbon, and this is always the case, in CO2 is equal to the mass of carbon over the mass of CO2 times 100% is equal to 12.01 U over 44.01 U times 100%. 12.01 divided by 44.01 times 100 is 27.3%. So out of that 58.74 grams, 27.3% of it is carbon. My percent hydrogen in H2O is equal to the mass of hydrogen over the mass of H2O times 100%. And I have two hydrogen, so it's 2 times 1.01 over 18.02. Remembering that we do have to double the mass of hydrogen because there is 2. And we get 11.2%. 27.3% carbon, 11.2% hydrogen. And those two values we always are going to use. So really we only have to do them once. Now we need to get the actual mass of carbon we have. Well, we have 58.74 grams of CO2, and we have 27.3 grams of carbon for every 100 grams of CO2. This is just a percentage, 27 over 100, 27.3 over 100, but I write it like this so my units cancel. So 58.74 times 27.3 divided by 100 equals 16.04 grams of carbon. We then take the water, 17.20 grams of water times 11.2 grams of hydrogen for every 100 grams of H2O, 17.2 times 11.2 divided by 100 equals 1.93 grams of hydrogen. Now I know my sample was equal to 20 grams, so what I'm going to do is I'm going to add those two values up and see if we're close to 20 grams, and clearly we're not going to be. 16.04 plus 1.93 gives me 17.97 grams of carbon and hydrogen. Well, this compound also has oxygen, so the mass of oxygen must be equal to 20 grams. Take away 17.97 grams. And that's 2.03 grams of oxygen. So what we have here is we have our masses. We have this much carbon, this much hydrogen, and this much oxygen, which must have come from the sample. So the final thing we really have to do is we have to just do an empirical formula question. So 16.04 grams of carbon, 1.93 grams of hydrogen, and 2.03 grams of oxygen. So I do all three of them at the same time. 1 mole of carbon is 12.01 grams of carbon. 1 mole of hydrogen is 1.01 grams of hydrogen. 1 mole of oxygen is 15.999 grams of oxygen. So we're just going to take those masses and we're going to convert them to moles so we can actually compare the number of particles. So 16.04 divided by 12.01 equals 1.34. I'm going to round a little bit. 1.93 is 1.91, and 2.03 divided by 15.999 equals 0.127. And take an extra decimal place there. And these are moles. Now, for an empirical formula, one of those has to be present in the fewest amount. So we're going to look and get the smallest one, which is oxygen. And we're going to divide each of those by that number. And really what we're trying to do is figure out which is present as one atom. We know that that's not always the case, that we could have atom molecule where there is no atom present in just one, but here we're going to hope that that's the case. So obviously the bottom one's going to be 1.91 divided by 0.127 is 15.04, so we're just going to round it to 15. Put a little approximate sign on it if we want. 1.34 divided by 0.127. And I get 10.5. Well, it's not ideal because one of the coefficients is 10.6, 10.5, it's at 10.55. So I'm going to have to multiply all of these by a coefficient, remembering that we got to multiply all of them to 0.5, so we'll use 2, so this becomes 21, 30, and 2. Nice and round numbers, so C, H, and O. It's C21, H30, O2. That's our empirical formula, and that is how we do combustion analysis.